Okay, so can you see my screen? Is my screen visible to you?
Yes, sir.
Okay, so uh, uh, last time we were discussing about this problem, and what is the problem? Which problem we were discussing last time? See this problem. Uh, Suppose f is a function, continuous function on R. S is a set of all points at which 0, and xn is a sequence in S, right? That means at each xn f of xn is 0. So what is our aim? X is in S. That means at x, if limit of xn is x, at x uh, function is 0. So our claim is f of x is equal. So statement of the problem is clear. Yes.
Yes, sir.
Okay. Now just recall what is sequential criteria for continuity. What is sequential criteria for continuity? Function f is continuous at a if and only if. Okay, what is sequential criteria? So f is continuous at a if and only for any sequence xn in domain of f uh, that converges to a, the sequence f of xn converges to what? Where f of xn will converge? Yes,
Of A.
converges to f of a. Right. So if xn is a sequence in the domain, if it converges to a, f of xn converges to f of a. So this is equivalent condition for sequential criteria. Okay, so if you understand sequential criteria, then solution of this above problem is easy. So what is given? So given that, okay, so what is given? F is continuous on R. Fine. Second, S is equal to set of those real numbers or in domain at which f of x is equal to 0. What is third? Xn is a sequence in S such that limit n tends to infinity xn is equal to x. So that is f of xn is 0 for all n and limit of xn is x. So this is given data. And what is our claim? X is also in S. We don't know. So sequence is in S, right? Sequence xn is a sequence of points in S, and uh, x and it converges to some number x. It may not converge in S, right? The sequence may not converge in S, but xn converges to x. Now we want to prove that x is member of S. That is what we want to prove. This is equivalent to proving that what? When x is member of S, which numbers are members of S? Yes, which elements are members of S?
Functional value is 0.
So value of function at x is 0. That is our aim. How to do this? This is our claim. Okay, before this, let us recall one more thing. Recall that f is continuous at a if and only for any sequence xn limit of xn is a implies limit of f of xn is f of a. Correct? Do you understand this?
Yes, sir.
But this is equivalent to saying that the limit of xn is a, that means sequence converges to a, implies limit of f of xn is f of a. But what is a? What is a? A is actually limit of xn. Do you understand? What is the sequential criteria? If xn converges to a, then we can interchange limit and f, right? We can interchange limit and f. So limit of f of xn means first we apply f and then limit. On right hand side, we first apply limit and then function. So we can interchange limit and function. So this is what the meaning of sequential criteria. So this is more clear. So okay, so since limit of xn is x, so where is x? Is x real number? Is x real number?
Yes, sir.
Right. And the function is continuous at x because it is given that function is continuous everywhere. So f is continuous at x. Function is continuous at x. Now see the previous discussion in black color. From that, what you can say. Therefore, so xn converges to x and function is continuous at x. Therefore, what is limit n tends to infinity f of xn? What is it? What is it? Just recall the previous sentence which I have written in black color.
F of x.
Yes, it is f of x or f of limit of xn. Same thing. So, but what is f of xn? But what is f of xn? But what is f of xn? What is the value of function at xn?
0.
0.
0 for all n. Right? Because we have chosen the sequence xn in S, and in S at every point function is 0. So at each n f of xn is 0. Therefore, what is limit n tends to infinity, f of xn is 0, but we know that it is f of x, right? Ultimately, what happens? Function value of function at x is 0, that means x is 0. So the problem is very simple, just sequential criteria, correct? Now there is one more interesting problem. Suppose f from R to R, suppose f is a function, R to R is a continuous function. Right, suppose this function is continuous everywhere on R, such that f of R is equal to 0 for R in Q. Suppose f is a continuous function and it is 0 at every rational. That is, f is 0 at every rational. So what is the information? Function is continuous and it is 0 at rational. From that, can you get more information? What is the value of function at irrational?
It must be equal to 0.
Right. Prove that f of x is equal to 0 for every x in R. That means at irrational also it is 0. And can you use the previous exercise?
Yes, sir.
Right. Do you see it is straightforward? So what is given data? Given data is f is continuous on R because everywhere it is continuous. And second given data is f of R is equal to 0 for every rational R, right? That is, what is f of half is 0, f of 3 by 5 is 0, etc. So at every rational function is 0. What is our claim? F is 0 at every irrational. Right. If you ensure that it is 0 at every irrational, then ultimately it is 0 everywhere because at rational already it is 0. That is, f of x is equal to 0 for every real. Right. If you show that it is 0 at irrational, then already at rational number it is 0, so it would be 0 everywhere. Correct. So how will you to prove that it is 0 at every rational, what I will do initially, how will I start my process? So let suppose alpha is an irrational number. What we want to show that f of alpha is 0. Right? I have chosen an irrational number and then I want to prove that function is 0 at alpha. In the view of previous exercise, how will you do this?
We'll consider a sequence of rational numbers which converges to alpha.
Exactly. Right. So here s is equal to x such that f of x is equal to 0. So what is the 0 set of function? It is rationals because at every rational function is 0. right? So take a sequence of numbers in S. So let Xn be a sequence of rational numbers such that limit of this sequence is alpha, right? So given that f is continuous at alpha, why f is continuous at alpha? What is the reason f is continuous at
F is
alpha?
given continuous for all r.
Right, so everywhere it is given to be continuous at alpha. We have chosen some real number which is irrational. So certainly function is continuous. And therefore, what is limit by sequential criteria? So if xn is a sequence of rational numbers, then what is f of xn? What is f of xn? Which xn is rational? So what is f of xn? Is it 0 for
0.
all n? Right, because each xn is rational and at rational function is given to be 0. So limit n tends to infinity f of xn. What is limit now? Each f xn is 0. So limit n tends to infinity 0 is 0. But by sequential criteria, it should be f of alpha. That means f of alpha should be 0. Because xn converges to alpha, f of xn must converge to f alpha. Right? Therefore, f is 0 at each rational, each irrational. Hence, fx is 0 for every x in R. So this is a speciality of continuous function, and there is some special property of rationals also, because if you choose any irrational, there is a sequence of rationals. That is what something is special property, so that this is true. Therefore, if continuous function which is 0 at rational, it is 0 everywhere. Right. So I will give exercise. Is suppose f is a function from R to R is a continuous function. Right? Suppose f is a continuous function such that f of R is equal to 5 for every rational R. So at every rational number function is 5, then what can you say about? Then prove that f of x is equal to 5 for every x in R. Do you see it is similar to the previous one?
Yes, sir.
So you should try to write down the proof. That means if function is continuous everywhere and you know the value of function at rational, certainly same is the value at irrational. Right? Constant actually. If it is constant at rationals and it is continuous, then function is constant. So therefore more general, if f is continuous and constant on Q, then f is constant on R. So this is a very interesting property, and here the rational property of rational plays an important role in this case. Fine. So now if you recall the limit of sequences if limit of xn is x, then does the sequence absolute value xn converge? Yes. If xn converges to x, what can you say about absolute value of xn?
It also converges.
So it converges to absolute value of x. That means it is absolute value of limit of xn. That means we can interchange limit and absolute value. Is same thing true for is the same true for continuity or function? That is the question. Is this true for limit, which we already discussed?
Yes, sir.
Right. Or before. Recall that if limit x tends to a fx is L implies limit x tends to a absolute value of fx is absolute value of L. Here also we can interchange limit and absolute value. So from this, can you make a statement for continuity? Suppose f is if f is continuous at if f is continuous at a, then can you say that absolute value of f is continuous at a? Is it true?
Yes, sir.
Right. And how will you write the proof? Suppose f is continuous at a. Therefore, what is our claim? Absolute value f is continuous at a. So this is our aim. Means what we wish. So that is what is our claim? Given epsilon, there exists delta such that distance between x and a less than delta, then distance between fx, absolute value of f minus absolute value of this is less than epsilon. Right. So given epsilon, but we know that f is continuous, so there exists delta such that whenever distance between x minus a less than delta, the distance between fx minus fa is less than epsilon because f is continuous. So note that the absolute value f minus absolute value of fa is less than or equal to absolute value of fx minus f of a by triangle inequality. Right? Therefore, if distance between x and a is less than delta, then distance between f of x and f of a, which is less than or equal to fx minus fa, which is less than epsilon. And therefore, we are successful to produce a delta for any epsilon, so that if distance between x and a is less than delta, then distance between absolute value fx minus absolute value of a is less than epsilon. Right, therefore, is continuous at a. So same idea you can extend. So if f from any set A to R is continuous, when I say function is continuous on set means it is continuous everywhere. A, then absolute value of f is continuous on A. So this is obvious, right? Because at every point this is going to be true. But question is the converse true? Is converse true? And what is the converse?
No, sir.
So that is if E is continuous, does this imply f is continuous? Right. And answer is of course no. Right. What is the example? Let us define function from R to R. So what is f of x? F of x is 1 if x is greater or equal 0, minus 1 if x is less than 0. Can you sketch the graph of this function? Is it defined everywhere on R?
Yes, sir.
Right. Now, if x is greater or equal 0, function is 1, and for less equal 0, it is less than 0, it is minus 1. So this is a graph of f. So therefore, what is absolute value f of x? If we take
1.
absolute value,
1.
means it is everywhere 1, right? Because even if x is less than 0, x is negative, value is minus 1, but it is absolute value of plus minus 1. Either value is plus 1 or minus 1, every time it is 1 for all x in R. Right? And how is the graph of absolute value function? So positive part and negative part. So, but if you take absolute value, negative part becomes positive. It was negative, but now it becomes positive because I am taking absolute value and positive part as it is. So this is absolute value of f. So, and is absolute value. So therefore, absolute value of f of x is equal to x for every x in R. 1 for every x in R. So constant function. So constant function. Hence continuous everywhere. Right, everywhere it is continuous. Especially it is continuous. Especially it is continuous at 0. So, but f is not continuous at which point f fails to be continuous. And why f is not continuous at 0? That means this
Limit
is an
does not exist.
example of limit at 0 does not exist. So this is an example where absolute value f is not continuous. So converse of this theorem is not true. Right. Now, next result. So, or recall, if xn is greater or equal 0 for all n and limit n tends to infinity, xn is equal to x. Then what can we say about x? X is also greater or equal 0, correct? Yes.
Yes, sir.
And can you think about limit of square root of x? Can we think about limit of root x? And does this limit make sense? Or does this limit exist? Right?
Yes.
It is root x. Because each xn is non-negative, so we can take square root and then limit is this, which is actually square root of limit of xn, because it is limit of xn. Right. Now, we want to think about function. So, suppose f from a to r is a continuous function such that f of x is greater or equal 0 for every x in its domain. This is a non-negative function. So, then can I say that square root of f of x is also continuous?
Yes, sir.
Right. So, if f is continuous on any point, then square root function is also continuous if function is greater or equal 0. So, proof is, and to prove this, I will give you hint which we already discussed. What we discussed, if limit x tends to a, f of x is L, and if L is positive or greater or equal 0, right, and function is non-negative, then what is limit x tends to a square root of fx is square root of. So in this way you can think about. So at what point square root function is continuous? The points where f is continuous and f is non-zero. This is what you can think about. So for example, so let f of x is equal to square root of x square minus 1 upon x minus 1. Then determine the state, not x minus 2, x plus. Determine the state of points at which f is continuous. Question is clear?
Yes, sir.
Okay. So, okay, let us call this as function g and determine the set of points at which g is continuous. How will you look at this question? Let f of x is equal to x square minus 1 upon x plus 2. Suppose this is my function fx, right? So, if f of x is greater or equal 0, then what is gx square root of fx? At such x, right? If at such x f of x is greater or equal 0, then gx we can define it is to the square root of fx. Right. Now, second point, at what points f is continuous? F of x is equal to x square minus 1 upon x plus 2 is continuous at on. We said this function is continuous.
R minus 2.
Real
R
number
minus 2.
minus
Right. So continuous everywhere except at x is equal to minus 2. That is, f is continuous on R and remove minus 2. So except minus 2, everywhere it is continuous. So minus 2 and so on. Except this point, everywhere this function is continuous. Now, what is the second criteria? When gx is well defined, if square root of f exists, right? Now, so at what points f of x is greater or equal 0? If x square minus 1 upon x plus 2 is greater or equal 0. Yes. And at what point this function is non-negative? Yes.
so when either both are greater than 0 or both are negative.
Right. That is implies x square minus 1 is greater or equal 0 and x plus 2 greater or equal 0 or greater than 0. Denominator should be greater than 0 or x square minus 1 uh, less than or equal to 0 and x plus 2 is strictly greater than less than 0. That is, so this implies, so x square minus 1 greater than 0 means what? When x square minus 1 greater equals 0. If we try to sketch the graph of x square minus 1.
Less
So
than
you have
1
graph
or
of
greater than, less than minus 1 or greater
right,
than 1.
minus 1 1. So for this is a graph of x square minus 1, and where the graph is positive or above x-axis, greater than 1, less than minus. Do you understand? This is the positive part. Right? So this red color part is positive, and which is possible for x. So therefore, this is true. So x belongs to minus infinity to minus 1 union 1 to infinity or x plus 2 greater than 0. That means or means what? And, not or, is and. Right. First condition is okay. So what is first condition or second condition? What is the first condition? X square minus 1 greater equal 0 and x square minus 1 greater equal 0 means x is in minus infinity to minus 1 union 1 to infinity and x greater than minus 2. But what is the and means? What is the intersection of first condition?
Minus 2 to minus 1, union 1 to infinity.
So x between x is in this x is in this red region. So x is in this red region, and it is greater than -2. So where is -2? -2 is here, and x is greater than -2. If you see the figure, then, what is the intersection of these two things, which is equivalent to x is in what? -2 -1 union 1 to infinity. This is the first. Or what is second? What is second? X square -1 less equals 0 means what? X belongs to -1 to 1, right? And x less than -2. But is it possible that x is in -1 to 1 and x is less than -2? Is it possible?
No, sir.
No, sir.
So in this case, no x. So in this case, no x exists. So only first case gives us the points. Thus, what is the conclusion of this? F of x is greater or equal 0 if and only if x is in -2 to -1 union 1 to infinity. Okay, so let us call this set as A, right? Hence, for x is in A, f of x is greater or equal 0. But therefore square root exists. But at what point f is continuous? At what point f is continuous? Except -2. And -2 is already excluded in this set A, right? And f is continuous on -infinity to -2 union -2 to infinity. And therefore, the gx is equal to square root of f of x is continuous on what? Which set?
Intersection of A and the
Right.
set on which f is continuous.
So let us call this as B. Continuous on, because we want both of these condition and, right? And what is this set? What is the intersection B? What is the intersection B?
A.
A, because A is subset of B, right? Yes.
Yes, sir.
Therefore, this B is continuous on. So you have to go step by step and understand the continuity of function on or any kind of function. But this can be understood easily. So due to next theorem. So what is a composite function? What is composite function? Suppose f is a function from A to B and g is a function from B to C, then composite of f and g is the composite f is a function from A to C. Let's say that how this composition is defined. How this composition is defined. So this is A, this is B, this is C. So F G. So G is from B to C, and if we choose any X here, what I get Y in B, which is f of X. Right? If we apply f on X, I get element Y, which is in B, and can I apply G to Y? Right?
Yes, sir.
And what is the image of Y? Let us call this image as Z, which is G of Y. And therefore, if you look at directly from A to C, right, what is the direct image? So, what is the direct image? So, direct image is called as G composite F. And what it gives, it directly sends X to Z. Right? How it sends? X goes to Y and Y goes to Z. That means what is G composite F of X is G of Fx, right? G of Y, Fx is Y and is Z. So G of Y is equal to Z. So that how composition is defined. How composition is defined from A to C? Go from so try to understand this logically. How do we define the composition? We first go from X to Y and Y goes from Y to Z. That is a way, but we can directly see from X to Z. That is what composition. Now, question arises: if F and G are continuous, is composition continuous? Right? Suppose F from A to R. Okay, so let me make it simple. B and G from B to C are functions. So now let A belongs to A, right? Then where is f of A?
B.
In B, because image of every element in A under F is in B. So if F is continuous at A and so G is continuous at B, which is value of function at A, then composite function C composite F from A to C is continuous at A. Statement is clear? Right. So what this statement says, I have said A, I have said B and C. This is F, this is G, and I am looking at A. What is B is F of A, which the image of A under F lands in B. Now we can apply G to B, right? So if F is continuous at A and G is continuous at B, then the composite function G composite F is continuous at A, right? So okay, so what is given? What is given is continuous at A and E is at B is equal to f of what is B? B is the image of A and G is continuous at this image. What is our claim? E composite F. Let us call this as H. Let us call this as H. H is equal to G composite H is continuous at A. So what is the way how to start? That is given epsilon where exists delta such that so what do we so given any epsilon we can produce delta such that whenever then distance of hx from what is less than epsilon, right? Is it clear? Is it correct what I am saying? Yes.
Yes, sir.
So this is what we expect. That means the composite f of x minus the composite f of a is less than epsilon. This is what we expect. So how to initiate the process? How to start the proof? How to start the proof? Yes. Given epsilon. And now what is aim? What we want? Delta.
Delta.
Right? Because so composite function or h, we want to prove that h is continuous at a. So given epsilon, we want to produce delta. Whenever distance of x from a is less than delta, hx from h is less than epsilon. Okay. So, but what is our assumption? What is our assumption? Let me draw the figure differently. This is my state B, and this is R or C somewhere, and here my state A, and I am here at A, here B, which is f of A. This is my function f, and this is function g. Okay, so epsilon is given. So since g is at B, so is it true g is continuous at B? Am I right?
Yes, sir.
So epsilon is already given. Can I say that there exists some number? Let us call it as eta, such that whenever distance of y from B is okay, basically y is in B, and distance of y from B is less than eta, then can I say that distance of gy from GB is less than epsilon? Is it possible? Yes,
Yes.
it is possible. So suppose g of B is somewhere here, and this is B. So there is eta. So t plus eta, t minus eta. If y is in this neighborhood, then here I have epsilon. So what is this? E of b minus epsilon e of b plus epsilon. So if y is here, e of y is here in this range. This is the situation. Fine. So given epsilon, we produce eta. But now we are going backtracking, right? We are backtracking the delta. So now we found eta. So now we got eta neighborhood of b. So also f is continuous at a for eta. Now eta is a positive number and f is continuous at a. So picture is in front of you. And now we have a neighborhood of f of a, which is eta neighborhood. Right, neighborhood of a, b means neighborhood of f of a. So for eta, can I say that there exists delta such that whenever distance of x from e is less than delta, then distance of f of x from f of a means b is less than eta. Is it possible? Yes. Okay, so now see the figure again. So now I found delta a minus delta a plus delta. So this is delta neighborhood. So if x is in delta neighborhood of a, then f of x is in eta neighborhood of b, which is f of b. Right. So thus from 1 and 2. So now if we combine expression 1 and 2. So thus from 1 and 2. From expression 1 and 2. Distance of x from a is less than delta. Then what happens? Distance of fx and fa is less than eta. But what is f of x? F of x is in b, which is a domain of g. Can I say that y minus b is less than eta? Yes.
Yes, sir.
But then if distance and y is in b, or f y is equal to f of x is in b. Now if distance of y from b is less than eta, then can I say that distance of g of y and g of b is less than epsilon? Is it true?
Yes, sir.
By 1. So this is by 2 and this is by expression 1. Right. But then what is y? Y is actually fx. And what is b? What is b? F of a. Means ultimately what we get, g composite f of x minus g composite f at a is less than epsilon. Ultimately what we found, therefore, whenever distance of x from a is less than delta, then distance of g composite f at x and g composite f at a is less than epsilon. Right? Therefore, for every epsilon, can we produce delta?
Yes, sir.
Therefore, composite function is continuous. Right? If you see the figure, above figure, so we first we were given epsilon. For that we found eta, and that means eta neighborhood of b. For eta neighborhood, we found delta neighborhood. So this is a backward way. So we can backtracking from epsilon to delta. So this process, once you understand, then proof is very straightforward. Right. So two functions are continuous, their composition is continuous. So next time we'll see the applications of this. and some more on continuous function. So if you have any doubts, you can ask. Yes. Any doubt?
No, sir.
So therefore we'll stop here. Then next time we'll see the applications of this composite. Right?